Okay, this is AP, AB, and BC Calculus, and we are doing the last section in Unit 5, which is 512, Exploring the Behaviors of Implicit Relations. So basically here what we're going to be doing is we're going to be doing implicit differentiation, but looking at the curves the same way that we looked at f and f prime and f double prime, but in curves where the curves are in terms of both x and y. So let's go ahead and move forward. So let's compare functions and implicit relations right now with the stuff that we already know. So we already know the stuff that's in this column, right? We know that the critical numbers for a function are when f prime, so if the function is f of x, right, the critical numbers for that function are when f prime, the derivative of f of x, is 0, or f prime does not exist. We know that if f prime of x is 0, then f of x has a horizontal tangent line. We know that if f prime of x is greater than 0, the function f of x is increasing. If f prime of x is less than 0, the function f of x is decreasing. We know that key points, which is a Hoganism, are when the second derivative of a function, so f double prime, is equal to 0, and that we can determine the concavity of f of x using f double prime, because if f double prime is greater than 0, like right here, then the function f is concave up, and if f double prime is less than 0, the function is concave down. All of these same things apply for implicit relations, except instead of talking about f's and f primes and f double primes, we're talking about, in place of f prime, we're talking about dy dx, which might be written in terms of just x, but it could also be written in terms of x and y, or just y. So if you replace all of these f primes with dy dx, you get the same concept, right? Dy dx is another way to write the derivative. And similarly, if we replace all these f double primes with d squared y dx squared, which is another way to write the second derivative. Oh, and also I should have written does not exist here for both of these. My bad, just noticed. So, just like I did up here, right? Does not exist is also an option for the second derivative. So anyway, so knowing that, we're really just applying a skill that we're already really good at. We already know how to find extrema. We know how to use the second derivative test if need be, and use the first derivative test. I will say that with implicit relations, sign charts are very tricky, so you're going to find that you use the second derivative test a lot more, okay? So when you're doing implicit relations instead of functions that you're used to, you will find that sign charts are very, very difficult. You will rarely, if ever, use a sign chart. Instead of sign charts, you will often use the second derivative test to determine extrema. So let's just dig right in and do a bunch of problems. All right, so consider the curve x squared minus 6x x squared y minus 6x equals negative 3. At 1, 3, does the curve have a maximum, minimum, or neither? Justify your answer. So the easiest way to determine this is to first start by finding the first derivative, right? So it is very likely that I'm being asked to do the second derivative test. Because again, if something's an implicit relation, it's very hard to make a sign chart. So I'm going to go ahead and differentiate, right? So you can actually solve this for y if you want. You don't have to treat this as implicit. There's only the one y. If you want to solve it for y, you absolutely can. If you choose to solve this for y, right, you would add the 6x over and then divide everybody by x squared, and that's absolutely fine. If that's something you want to do, you could totally do it. If you don't want to solve for y, you don't have to. So in this instance, I'm just going to go for it and not solve for y, right? I'm going to do this implicitly, but you certainly don't have to. So when I differentiate, I'm going to get u dv plus v du, which is going to be a 2x, right, minus the 6 equals a 0, right? And now I'm going to solve for dy dx. So I'm going to get x squared dy dx equals, I'm going to add that 6x over, or add the 6 over rather, and subtract this 2xy. So I'm going to get 6 minus 2xy all over that x squared that I'm going to divide over to get rid of it. Okay, so I get that my dy dx equals 6 minus 2xy on top of an x squared. So the first thing I need to check is, in order to have a max or a min, I need the first derivative to be 0. So if there's an extremum of any kind, right, if there's an extremum of any kind, then I need dy dx of this 1, 3 to equal 0. So the question is, does it? Let's start there, because I'm not even going to bother to find the second derivative until I know if that's true. So dy dx, and I'm going to write this evaluated at 1, 3 bar, right? And I'm going to plug in 6 minus 2 times 1 times 3 over a 1 squared. Sure enough, that is a 0 over 1. Yep, that's 0. Okay, cool. So now, it's possible that I can do the second derivative test. So what I'm going to do is I'm going to differentiate again. So I'm going to take this dy dx equals 6 minus 2xy all over an x squared. And it's up to you. Interestingly enough, you could actually clean this up a little bit if you want. You could make this a 6 over an x squared minus a 2xy over x squared, which is a little bit nicer because you could make it a 6x to the negative second, and you could cancel one of these x's. You could make it a minus 2y over x. You don't have to, but I think that could be a little nicer. When I differentiate again, and you're not always going to be able to do that, but when I differentiate again, I'm going to go ahead and get that this is a negative 12x to the negative third, right? I don't know if that was better or worse. Either way. And then this is going to be a quotient. Now I'm gonna leave this minus out in front of the quotient rule. Okay, this is my high function and this is my low function. So I'm going to get minus. So my quotient rule is going to be low. D high is going to be a negative 2 dy dx, right? Minus high, which is the oh, sorry, I kept the negative up front. It's just a positive. My bad. See, this is why you have to pay attention to what you're doing. I lied. I'm going to make that a plus and a minus because I clearly can't handle it. So we're going to make that a minus. I'm going to keep the negative. So minus high, which is the negative 2y. D low is a 1, right? Draw the line, square the low. Cool. All right, so keep in mind that I don't care what d squared y dx squared is all the time. I literally only care at 1, 3. So it's up to you. Right? It's up to you if you want to plug in or not. There is an advantage to doing this as just a quotient rule, and the advantage is that it does kind of come out to be easier whether this thing is positive or negative, but we'll go ahead and do this. So, so this is an x cubed on the bottom, so that's just a 1, right? Plus, when I plug into this, I'm going to get x minus, so this is a negative 2 times a 0, because we've already established that dy dx at 1, 3 is 0, right? This will be a plus 2 times y, right? All over 1 squared. So I end up getting that this is a negative 12 plus what seems to be a 6. So I get negative 6, which is less than 0. Remember, if my graph is concave down and flat, that's a max. So since dy dx evaluated at 1, 3 was 0, and d squared y dx squared evaluated at 1, 3 was less than 0, it's a max. Cool. So again, this is one of those instances where it's easier to do the second derivative test. You could have solved this for y. This is an example of one that you could solve for y if you wanted. I chose not to. All right. Go ahead and give P1 a try. You're going to consider the curve x squared plus y squared equals 4, and it's the same question, except it's at the point 0, negative 2. So I'm going to go ahead and start differentiating, right? So I'm going to get 2x plus 2y dy dx equals 0. dy dx seems to be a negative 2x over 2y, which I'm just going to write as a negative x over y. So the first thing I have to check is dy dx evaluated at 0, negative 2 a 0? Well, when I plug in dy dx evaluated at 0, negative 2, I get negative 0 over negative 2, which is 0. Yes. Cool. So now I'm going to differentiate again. So d squared y dx squared. Now I need to do the quotient rule, right? I have a high and I have a low. So low d high minus high d low. Draw the line, square the low. So again, I don't really care to clean this up at all because I don't want d squared y dx squared all the time. I just wanted it at a very specific point. I wanted it 0, negative 2. So I'm going to get negative 2 times negative 1 minus a negative 0 times a 0, because we already established that dy dx was 0, right, at this point, all over a 4, right, because it'd be negative 2 squared. So I seem to get 2 on top of 4, which is greater than 0. So since dy dx evaluated at 0, negative 2 was 0, and d squared y dx squared evaluated at 0, negative 2 was greater than 0. And if you need that picture, you can see concave up here. It is a minimum. And I know I told you to avoid using pronouns but you're answering the direct question, does the curve have a max, min, or neither? So you're answering the question. You could say the curve has if you want to be fancier. All right, next question, E2. Write the equation of the line tangent to the curve. Okay, so if you hear equation of a line, your brain should instantly jump to two things. You need a point, of which I seem to have half. I have x is -2, so we'll talk about that in a sec. And you need a slope, which in calculus means a derivative, right? So my point, I'm going to find by plugging in x, right? So let's go ahead and find the point first, because that doesn't involve any calculus, right? So to find the point, I'm going to plug in -2 squared and get a +4 over y cubed equals -4, right? 4 equals -4y cubed. -1 equals y cubed, so y is a -1, right? That's how cube roots work. So I get the point is -2 comma -1. To find the slope, I need dy dx, right? So I'm going to need dy dx evaluated at the -2, -1. So to do that, I really need to find dy dx first, right? So it's up to you. If you don't want to do a quotient rule, I'm going to argue that this is not a good case for a quotient rule. I'm going to argue it makes way more sense to multiply the annoying y cubed over, and now there's no quotient rule, right? So now there's no quotient, and that's super nice. So when I differentiate, I get 2x equals -12y squared dy dx, and I can divide that over and get 2x over -12y now y squared. Now remember, we simplify selfishly. I think it's worth canceling the 2's. It's your call. So that's my dy dx. So my tangent slope is going to be dy dx evaluated at -2, -1, which you have to write. You need to write that you're plugging in values. So you're going to get -2 over a -6, which is a 1/3, right? Because the -1 squared is still going to come out positive. So then I need to make sure I answer my question. The question originally said write the equation of the tangent line. It didn't ask you to do anything else. So my answer is y minus the y value, which would be y minus a -1, equals my m, 1/3, x minus the x value, which would be x minus a -2. Now, most of the time you'll see it written with the 1 subtracted over because you often are going to be asked to use a tangent line to estimate. There is no incentive to distribute the 1/3. All right, next question. Same idea, write me the equation of a tangent line. Feel free to pause me if you want. All right, so first thing I need is a point. I'm going to find that point not using calculus because there's no reason to use calculus to do it. So when I plug in pi, right, I'm going to get x cubed cosine of pi equals 8. That's x cubed times -1 is 8. X cubed is a -8. So x, y is pi. Whew, come on, Hogan. I knew I meant to plug the pi into the cosine, but look, I wasn't paying attention. It's y is pi. Oops. So I get x is -2. So that was tricky of me, and I basically fell for it. All right, so I get x is -2 and y is pi. So that's the first thing I need. The second thing I need is a slope. So in order to find the slope, I really need dy dx. Well, here I can't really get out of the product rule without taking an inverse cosine, which frankly you just don't want to do. So u dv, derivative of cosine is going to be negative sine, right, times the derivative of that stuff, which is a dy dx, plus v, which is cosine y, du, which is going to be a 3x squared, equals a 0 because that's an 8 on the other side. I want to solve for dy dx, so I'm going to get that dy dx equals, I'm going to move this 3x squared cosine y over by subtracting it, right, and then I'm going to divide by all the stuff that's sitting in front of the dy dx, right? And you can cancel a negative if you want, that's fine. There's not a whole lot of reason to do much work because I'm about to plug in -2 comma pi, right? All I need to do is plug in, that's my whole job. So when I do that, I'm going to get, again, if you want to cancel a negative, you can. I get a -3 times a +4 times a -1 because that's what cosine pi is, right? Ooh, this is tricky. I get a -8, right? I get a -8. And then when I plug in sine of pi, I get 0. So I end up getting that my slope is undefined. So this is tricky because you do all that and you're like, uh-oh, what do I do? My slope's undefined. Well, the answer is that if something's undefined, right, it has a vertical tangent line. So undefined means a vertical tangent line that goes through the point -2 comma pi, Well, vertical lines are the coordinate x equals, so my answer, after all that work, despite the fact that I had to find dy dx to find this, is just x equals -2, because that's the vertical line. If you picture where -2 comma pi is, remember that pi is somewhere around 3, so this is the dot you're kind of looking at, right? There's your vertical line. It's x equals -2. So that's kind of crazy, because sometimes you do all that work just to get an answer that looks like that, but when you get that, your brain probably kind of chokes for a second, and you think, oh, what do I do? Well, that's what you do. All right. Describe the concavity of the given curve in quadrant 1. Justify your answer. Okay, so when you read this, you need to think, okay, concavity is talking about the second derivative, right? So concavity is talking about the second derivative and its sign, right? So in this case, I'm going to have to bust out my derivatives to get to d squared y dx squared, and for some reason, I'm being told that it matters what quadrant we're in. So let's go ahead and figure that out. It's up to you. It does make your life a little easier if you move stuff to the other side so that y is mostly by itself, but it's up to you. I'm not going to do that here. So 12x cubed plus 10y dy dx equals 0. When I subtract the 12x cubed over and divide by the 10y, I get dy dx equals negative 12x cubed divided, sorry, I said negative and didn't write it, divided by 10y. I would suggest that you cancel the 2's out. It really does make your life a lot easier. You're doing things selfishly, right? That's the goal in this stuff. Okay, so there's my first derivative. When I go to do the second derivative, I now have a high function and a low function. So d squared y dx squared is going to be low. D high is going to be a negative 18x squared, right? Minus high, which is a negative 6x cubed. D low, which is going to be a 5 dy dx. We'll deal with that in a sec. Draw the line, square the low. So 5y quantity squared. So we're going to clean this up. Among other things, we're going to need to replace this dy dx with this thing. So I'm going to get that this d squared y dx squared is a negative 90 x squared y, right? So then when I replace this thing, this is a negative 6x cubed over 5y, right? I'm going to have negative times a negative times a negative. So it's going to come out negative. And then it seems to me like I can cancel. So I have a 6 times a 6, which is a 36. And then the 5 on the top and the 5 on the bottom cancel. So I get a 36 x to the 6th over y, right? Because it's this thing times this thing times this thing, and then I cancel the 5's. Okay, and on the bottom, I have a 25y squared. So I could, if I want, I can get a common denominator on the top. Like, it's definitely something you do sometimes. I'm going to argue at this moment, I can tell you that this curve is always concave down in quadrant 1. Here's my reasoning. In quadrant 1, x is greater than 0 and y is also greater than 0. Well, this denominator is going to be positive anyway, as long as y is not 0. If both of these numbers are positive, if x is positive and y is positive, this is a positive number with a negative in front of it, so it's going to come out negative. These guys are both positive numbers, so this whole thing's going to come out negative. So my argument is the entire numerator comes out negative, right? So my argument is that in quadrant 1, d squared y dx squared is less than 0, so the curve is concave down. Now, you'll also see that there are times when you're going to want to get a common denominator here and clean this up, and you absolutely can, and there's nothing wrong with that. The common denominator would involve being over y, so I would end up with 90x squared y squared minus 36x cubed, sorry, x to the 6, my bad, all over y, all over a 25y squared. So if you really cleaned this up, it would be a negative 90x squared y squared minus 36x to the 6th, and then that y on the bottom would end up down here at the bottom with the other y's. Again, I'm going to make the same argument that what's going to happen is you're going to get to this stage where you recognize that in quadrant 1, where x's and y's are all positive, this thing nets negative, which means that the curve is concave down. All right, so give the same thing a try in P3. Here you're in quadrant 2. Remember that quadrant 2 is here, right? So in quadrant 2, the x's are negatives and the y's are positives. Again, this is one where if you want, you could solve this for y. You don't have to do this implicitly, right? You could make this y equals 18 over x squared, and that makes your life an awful lot easier, right? Or you can do it implicitly. It really doesn't matter. So you're going to get dy dx equals a negative 36x to the negative third, right? Which means your d squared y dx squared is going to be a negative, why is my brain broken? 108, sorry, positive 108, x to the negative fourth. So 108 over x to the fourth. Well, in quadrant 2, right, in quadrant 2, x is less than 0, but x to the fourth would be greater than 0. So d squared y dx squared is going to be greater than 0. So the curve is concave up. Now, let's say you had not been able to solve that for y, right? So that's my answer, right? And that's my justification. If you had not solved it for y, so let's just do this as though you had done a product rule. If you had not solved for y, you would have done your product rule, and I promise it comes out the same way. So you would get u dv plus v du, right? When you solve, you'd subtract this over, right? So you'd get dy dx equals a negative 2xy over an x squared, which you're probably going to rewrite as a negative 2y over x. Now you have a high and a low function, right? So when you differentiate again, d squared y dx squared, you get low. D high is a negative 2 dy dx minus high, which is negative 2y, d low. Draw the line, square the low, right? You would replace your dy dx, right? So you'd replace your dy dx with this. So this would be an x times a negative 2 times a negative 2y over x plus a 2y all over an x squared. So you get that this is a 4. The x's will cancel, so 4y plus 2y all over x squared, which is a 6y over x squared. Since you are in quadrant 2, right, so in quadrant 2, y is greater than 0, x is less than 0, so you would get a positive on top of another positive because it's squared. So it would net positive, and then you would get back to the same answer that I gave you way up here. There it is. All right. All right, E4, and then we're going to do a P4, and that's it for Unit 5. So given the derivative of an implicit relation, so you're already given the derivative, and that the point 1, 2 is on the original curve, right? X comma y, 1, 2 is on the original curve. Write the equation for the tangent line at 1 comma 2. Okay, so remember, right, the equation for a tangent line, you need two things. Number one, you need a point, but they just gave it to you. Yay. Number two, you need a slope, which is going to be the derivative evaluated at that point. So when we go to do A, right, I have my point. That was very nice of them to give me 1 comma 2. I know that my slope should be dy dx evaluated at 1 comma 2. Well, that's going to be 1 squared plus 2 squared, which is definitely a 5. So my answer is y minus the y value equals m x minus the x value, although I would suggest that you add the 2 over. So 5 x minus 1 plus 2. I would suggest that you do that because very frequently you're asked to use your tangent line. Oh, look, that's what's happening in B. Use the tangent line you made to approximate at x is 1.3. All right, so for B, so y is approximately 5 times 1.3 minus 1 plus a 2, right? So that's going to be a 5 times a 0.3 plus a 2, which is a 1.5, right? Plus a 2, so 3.5. All right, so this last bit is about concavity. So is your approximation, it should say approximation, not approximate. Anyway, is your approximation in part B an over or underestimate justify your answer? So think about it this way. If a curve is concave up, then the tangent line approximations fall under it, right? And if a curve is concave down, then the tangent line approximations go over it. So what part C is asking you is about the concavity. So you're going to have to differentiate a second time. So we know that dy dx was x squared plus y squared. So we're going to need to find d squared y dx squared, which is going to be 2x plus 2y dy dx, right? And that's the big mistake is people forget the dy dx, which is a 2x plus a 2y times x squared plus y squared. Okay, so the question is, what's happening at 1, 2? Well, think about it this way. 1, 2 is in quadrant 1. So in quadrant 1, x's and y's are all positive. See how these are all plus signs, right? They're all plus signs, and we're in quadrant 1, which means that in quadrant 1, where x's and y's are both positive, d squared y dx squared is a whole bunch of positive things plus a whole bunch of other positive things times some positive things. It's definitely positive. So the curve is concave up, right? And we've seen, if I scroll back up for a sec, concave up means that the value you estimated is an underestimate. So the tangent line approximation is an underestimate. Right now, and again, I think I've said this in previous videos, for 20 plus years, I've had to draw this to make sure I'm right about it being an underestimate, right? So this would be the actual, this would be the estimate. And you can see that if something's concave down, the opposite is true, right? Here's the actual, here's the estimate. So again, that's your answer. You need to use the second derivative to justify it. Okay. All right, so very last problem of the last section of this unit, P4, given the derivative of an implicit relation and that the point -3, -4 is on that curve, write an equation for the tangent line to the curve at -3, -4. So here's your point, right? There's your point, right? For part A, we know that we can find our slope by evaluating dy dx at the given point, -3, -4. So that's going to end up giving me a 9 minus a -64, right, which should give me a 73. So in A, I'm going to get y minus the y value, which will be y plus 4, equals 73, x minus the x value, which will be x plus 3. But we're probably going to go ahead and solve for y by subtracting the 4 over because it makes life a lot easier when you do what's likely to be the next part of the problem, which is going to be to use your equation. So there's your tangent line equation. Sure enough, B asks us to use the tangent line equation at -2.9. So I'm going to get 73 times a 0.1 minus a 4, which is a 7.3 minus 4, or a 3.3. It's my approximate value. And then the last part is this an under or overestimate? Remember that that question is about concavity, because if your curve is concave down, the tangent line is an overestimate. If your curve is concave up, the tangent line is an underestimate, right? So really they're asking us about concavity here. Oh, you can ignore that. That's incorrect work from before. All right, so since this is asking us about concavity, d squared y dx squared is going to be a 2x minus 3y squared dy dx, right, which is really a 2x minus 3y squared times an x squared minus y cubed. So if I clean that up a little bit, right, d squared y dx squared, I'm going to get a 2x minus a 3x squared y squared, right, plus a 3y to the fifth. Now, keep in mind that we're looking at -3, -4, which is squarely in quadrant 3, right? Here's -3, -4. We're in quadrant 3 where x's are negative and y's are negative. So if we look at this, this will be a negative value in quadrant 3 because 2 times negative number would be negative. This will be a -3 times a bunch of positive because that stuff's squared. So this thing will also net a negative value. And then because the y's are also negative in quadrant 3, this will also net negative, meaning if you add 3 negative things together, what you can figure out is that in quadrant 3, right, in quadrant 3, which is where we are, d squared y dx squared is less than 0. So knowing that, if we come back up here for a sec, right, knowing that in quadrant 3, so my answer to C, we'll squeeze it in here, d squared y dx squared is less than 0 in quadrant 3, So the curve is concave down. Thus, we have an overestimate, right? Overestimate, because then you can picture that again for decades of doing this. I've had to draw that and say, oh, concave down means that the answer is an overestimate. And that's my answer. So that is your Unit 5.